Hi, everybody. Now it's time for us to start talking about electric fields. This is the first time we've really started talking about the concept of a field, but it's going to be really central to all of electricity and magnetism going forward. We could have used it back with gravity and talked about a gravitational field. It was simply not particularly necessary at the time, and it was a complication. At this point, it has become necessary. It was the development of the idea of electric and magnetic fields in the 1860s that led James Clerk Maxwell to ultimately be able to unify all electricity and magnetism to four simple equations. It was a really revolutionary concept at the time, and it's a little bit of an abstract leap to get there. Once you get used to them, once you've worked with them for a little while, they're sort of second nature. I mean, you talk to almost any physicist or anybody else that works with electric fields, and you talk about it as being some kind of weird thing, and we'll just blink and look at you because we're just used to them, and they just make total sense, and we can picture them. But it does take a little while to get there. So work on visualizing these things and try to keep remembering what they are for the next few weeks, and eventually they'll come, and then you'll be able to use them really easily. Before we talk about electric fields, I actually want to talk about a gravitational field for a minute, though. So I want you to picture this situation. Euclid the duck, who I'm probably not going to be able to draw very well today. Oops, that's a terrible duck. Give her a little bill, maybe. Oh, that's better. There's Euclid. She's flying around our classroom, okay? Everywhere she goes, she feels some force downward. The force in the duck, okay? And it's always downward no matter where she goes, okay? And it's always the same magnitude no matter where she goes. That's a terrible F. Okay, so there's kind of this, if you picture the set of arrows everywhere in the room pointing down, okay, that all have the magnitude of the force in the duck. Now, if Euler the dragon, who I really don't think I can draw, teeth, big snout, dragon. We'll leave that as the dragon. She'll have some fire. Okay, if she goes everywhere, there's going to be some bigger force down, force on the dragon. Okay, and that also exists everywhere from every point. Okay, so if you talk to these two, or they talk to each other later on about the gravity in the room, Euclid will say, well, that there's a force of gravity equal to, it's like 1.5 newtons is what she feels. And Euler the dragon feels like 20 newtons, and they have no real agreement about that. Now, there's no reason they have to, of course, as you know. Heavier things are heavier because they have more force of gravity on them. But it does seem a little bit weird that there's nothing common to them. Okay? Now, secretly in your brains, you know there's something that is the same for both of them, and that is the acceleration that they feel. And we're going to come back to that in a second. But first, I want to talk about what they would feel if they went all the way around the Earth. So if they went around the Earth, Euclid would go around and she'd find a force of gravity vector that's always pointed towards the middle of the Earth. Okay? But always, if she was at the Earth's surface, always had the same magnitude. If she moved farther away from the Earth, she would have smaller vectors. Okay? Eventually, they get really small, just kind of basically points. Okay, so she's got this mapped out picture of these vectors of gravity everywhere. But then Euler the dragon comes along and does the same thing, and she finds bigger forces everywhere. Okay, so again, they have this situation where they disagree. Now, at some point when they're talking, they're going to talk about the acceleration they feel, and they're going to realize they always feel the same acceleration, no matter where they're at. If they measure the same point, they'll always have the same acceleration. And you start to say, well, maybe the thing we should be talking about with gravity isn't the force vector, it's the acceleration vector everywhere. Because everybody will have the same acceleration vector. And so we could just describe the acceleration vector everywhere in space for everybody. And if you want the force, all you do is you take the acceleration vector and you multiply by the mass. Okay? Now, this looks a lot like Newton's second law. This is not what I've just written down, actually Newton's second law, because this only is about gravity. Okay? It turns out that the equivalent to an electric field for gravity is actually the acceleration vector everywhere. It's not going to be quite this simple with electric fields. So let's go back to our point mass. Our point charge. Let's say we've got a positive point charge. Say a proton. Okay? And we take a really small charge. Well, let's not make it a proton. Let's make it really big so it doesn't feel the force here particularly. Let's make it 1,000 protons. Okay? And we take an electron everywhere. And we measure the force it feels. Okay? There's a force here, a force here, a force here, a force here. If we get closer, the force gets bigger. Okay? And so forth. Now, if we take a proton everywhere and measure the force, it will be the opposite everywhere. And so they have this disagreement again. But what you might have noticed about Coulomb's law, K Q1 Q2 over R squared, is there's this Q here. If we divide that Q out, that's the Q of the electron and the proton here. All we're left is this Q, okay? And that's the same for everybody everywhere in space. What we're left with is the electric field, which we define, this is a definition, is F over Q. It's the force everywhere divided by the charge at that point. And it turns out this is the same for everybody. It's not just true for Coulomb's law, it's true for an infinite sheet of charge, it's true for an infinite line of charge, it's true for any arrangement of charges. Okay, and it's the same in space for everybody. Everyone's sensing that electric field, essentially. Which means everybody could be given just the same electric field, and they're like, okay, if you want to find your force, you take your charge and multiply it by the electric field, and you'll get the force out. Okay? But it's the field that's everywhere in space. Okay? So, what does the field look like? Well, for this big positive charge, it points away everywhere. Okay? If we did a big negative charge, it would point towards it everywhere. Okay? Which is one of our rules for electric fields now. They always point away from positive charges and towards negative charges. If I were to have a positive and a negative charge near each other, the field would point away from the positive charge and end up being towards the negative charge. Okay? So you get these sort of field lines, ooh, there that goes, that run from positive to negative. Okay? This may be a somewhat familiar field diagram. You've probably seen it on magnets as well. Okay? Everywhere along these field lines, we could draw a line that's tangent, find the vector, that's the electric field vector, okay? And from that, we can work out the force is equal to Q electric field, okay? Once we know the Q of the charge right there, okay? If we swap that charge out with a different Q, we just go ahead and plug it in again, okay? So the idea here has been to replace our idea of the force everywhere with something that everybody agrees about, okay? The force was not universal for everybody feeling the electric, well, I keep wanting to use the word field because that's just the word for it, electric field. But the electric field is universal to everybody, which is really, really handy, okay? All right, that's the electric field. We'll talk about it also in class. I will see you, everybody, there. Good luck, and I hope this helped.